Swayam Prabha. Digital India. Educated India.
Shri Gurubhyo Namaha. It is my distinct honor to introduce our speaker today, Professor Mangalsundar Krishnan. Professor Krishnan is a professor emeritus in the Department of Chemistry at the Indian Institute of Technology, IIT Madras. With a PhD in theoretical chemistry from McGill University, Canada, he has dedicated decades to advancing research in molecular spectroscopy, computational chemistry, and quantum information. Beyond his deep scientific expertise, Professor Krishnan is a true pioneer of digital education in India. He served as the first National Web Courses Coordinator for the NPTEL, National Program on Technology Enhanced Learning, and has been a driving force behind RSIC. His work has fundamentally shaped how quality technical education is delivered and accessed across our country. His lifelong commitment to both scientific rigor and democratizing education serves as an inspiration to us all. Please join me in welcoming Professor Mangalsundar Krishnan.
Yeah, thank you. By the way, I do chemistry. That's my area of research. And physical chemistry, chemical physics, principles, and fundamental molecular spectroscopy, those are all my areas of research. Okay, so when somebody asks you what is emeritus, after retirement, if you are requested to continue, up to a certain period you can stay. Whereas some universities give you a title permanently. Post-retirement, if they say that you have done well and the university wants to retain you, they'll say you are emeritus, your lifetime. IISc does that, Indian Institute of Science does that. And some other, in IIT Madras, it's 5 years after your retirement. So I finished that this year. Okay. Now, today I realized that when I wanted to say something about matrices and vectors, I looked at the textbook, it looks like it is this year's portion, NCERT textbook. But have you had any introduction to them at all? Somebody says yes, somebody says no. Okay, 2 people say yes. How many of you have had some introduction to matrices? A few. Okay, that's less than half the class, okay, less than half the group. And how many of you have had interactions on vectors? Okay, that's slightly better. Okay, so I will do some introduction. The idea is not to jump to difficult parts. This program is not to tell you, all those difficult things immediately so that you go home, but to make you think while you are listening to some of these new ideas and some of these concepts. So vectors are essentially the way we have used them in physics, mathematics, and in engineering. Vectors are quantities, or you can say properties of matter. If it is vector, that has a direction and a magnitude. That's the first introduction to vector. So for example, if you draw an arrow on the board with an arrowhead, essentially what it means is that this can be written as, this is a vector by definition because it has a magnitude which is the length of the arrow and a direction which is the direction pointing. Force is a vector, okay? Velocity is a vector. Acceleration due to gravity is a vector. So there are physical quantities, and in chemistry, many other things are vectors, okay? So vectors have very special properties that one has to look at. What are not vectors? For example, numbers, scalars. They are called the scalars. Scalars are numbers, and multiplication of numbers is a very standard rule. All of you know the multiplication table. Whereas when you combine vectors, you have to follow certain basic rules, and there are 3 ways by which you can combine, other than adding vectors and other than subtracting vectors and so on. So if you add 2 vectors plus b, okay, and for example, if this is A and if this is B, okay, what is A plus B? diagonal. Okay, that's because it's A plus B. Okay, the sum of the vectors is what? This is a standard definition. What's the difference between A and B? It's the other diagonal, but which direction? Which direction? A is in this direction, minus B is in this direction, minus B plus A. So which is the direction? This one, in this direction, okay? A minus B. But then in addition to these kind of representations, we also write A and B in terms of coordinate systems, because that gives us a lot of flexibility in terms of dealing with vectors, because this way it is abstract. The moment you introduce coordinates, vectors and scalars and other quantities, vectors, more than vectors, they are called the tensors. All these quantities have certain basic properties that can be described using simple mathematics. Okay? So usually what one does is to introduce a coordinate system. For example, here you can write an x coordinate and a y coordinate. So let me do a two-dimensional vector, that is the vector on the board. It's not coming out. Okay? A vector pointing out like this. Okay? So we will draw two perpendicular axes, x and y, and we do this cyclically. Okay? It's more important the moment you go to 3 dimensions, but now x and y. And if you call this as a vector, there is a way of writing vectors in terms of the vector's projection on each of these axes. The projection of this vector, then ay multiplied by, if you draw this perpendicular here, ay, this length, okay, ay times y gives you the vector in this direction. Therefore, the sum of the ax times x and the ay times y gives you the vector a. Okay? So this is the decomposition of the vector in terms of simple coordinate framework. Ax, x plus ay, y. You call this as the vector a. Okay. Now, is this the correct way of drawing the coordinate, or what about if I draw another coordinate system which is perpendicular but with looks slightly differently? Okay? There's no reason why it should be like this. It can be any coordinate system, two-dimensional, orthogonal. They are called the perpendiculars or orthogonal to each other. Okay. Now you see this vector, if you draw, it's perpendicular, and if you call this as a unit vector x prime, okay, and you call this as a unit vector y prime, okay, then you see that the components ax prime, this is the perpendicular drawn on this axis. So this is ay prime, and the component, this is ax prime. That also describes the same vector. Okay, ax prime times x prime plus ay prime times y prime is also the vector a, because that's what this is. Okay, ax prime times x prime, ay prime times ay prime. Okay, so that is also ax prime, x prime plus ay prime, y prime. Therefore, how do we uniquely define a vector? There's no unique definition. Okay, you choose a coordinate system which is relevant to the study of the physics or the engineering or the mathematics of that problem. Okay, a choice of the coordinates allows you to do other things, namely, what is the relationship between these two and these two? If this vector has been tilted, this unit vector in this direction is tilted by an angle theta from the original axis, are these things related to each other? What is the length of this vector, by the way? In any coordinate system, you can choose this, for example. if you think about the length, it is nothing but square root of ax square plus ay square. Okay? The square is the square of the length. If you remove the square root, it's the square of the length. But what about in terms of the other coordinate system? That also is the same thing. Ay prime square. Therefore, you see the length is the same independently of whether you describe it in the xy coordinate system or you describe it in the x prime y prime coordinate system or x double prime y double prime some other angle. Okay. It's a plane, two-dimensional system. Therefore, this vector is like this. Maybe you can choose the x-axis and y-axis in these two directions outside the plane, but still all the three lines will form a plane. So that it doesn't matter whether the plane is on the board or it's elsewhere. Okay. So, for example, you choose a plane like this. Okay. And then you can draw x prime, y prime, some other basis coordinate system. It doesn't matter which plane you are in. Okay? So what is important for you is that a vector is described in different ways in different coordinate systems, but has two things which are common, namely the length of the vector and the direction of the vector. Okay? The direction is physical. If there is a force acting in this direction, that's physical. This direction is fixed. Now, how do you define this in terms of various coordinates is your choice. With this as a definition, this number, the magnitude is called a scalar and is invariant to the choice of the coordinate systems. It doesn't matter which coordinate system you use. Coordinate system is invariant. And it's called a scalar or vector of rank 0. Rank 0. A vector is a vector of rank 1. You don't say vector of rank 0, you say the general thing to say that is, of course, instead of this, you use the general word called a tensor. Tensors are general quantities, not just a direction, one direction and one magnitude and so on, but tensors are, they are also very important in physics and engineering, okay? And tensors are classified by their rank, and the rank 0 is called a scalar. The tensor of rank 1 is called a vector, and the tensor of rank 2 is a second rank tensor, third rank tensor, fourth rank tensor, and so on, okay? And each one of them is important in physics and chemistry, in physics and chemistry, and in systems engineering, very, very much, okay? Yeah, very much important. Now, two things are done. The first is to define a product of vectors. Of course, additional vectors is something all of us can do. And when you add, before doing this, when you add two vectors, A, which is in some coordinate system, ax plus ay, and you add the vector B, bx plus by, the addition A plus B adds the components coordinate wise. So it's ax plus bx of x plus ay by of y. So you have to add the components. Component wise you have to add them. And you can call this as a plus b of x vector. That is the x component of the sum a plus b. And this is the y component of the sum a plus b vector. So if you call this as C, for example, then this is Cx and Cy. Okay? That's what that is. This is with respect to addition and subtraction. Subtraction is the minus sign. Okay? Negative addition. But with respect to products, you have got three types of them. there is a scalar product which is symbolized by a dot between them, the two vectors, okay, or A or B, A dot B. For all classical mechanics and for all the purposes not quantum mechanical, A dot B is the same as B dot A. Okay. A dot A, we don't have a problem. Okay, so same as whichever way you write. And then this is called the scalar product. This is called the dot product. Dot scalar or a dot product. Okay. And then you have a vector product. The vector product is usually represented as A cross B. I didn't write A cross A because in the regular classical methods, A cross A is 0. Okay, it's not defined. But A and B, if they are two different vectors, A cross B is definable, provided A and B are not parallel to each other. Okay, if A and B are parallel to each other, A cross B is 0. Again, classical, not quantum mechanical. Okay. In quantum mechanics, you can have vector cross product with its own themselves. The most famous one is the angular momentum vector. Okay. J cross J is not 0. They are called pseudo vectors. Okay. So this is the cross product. And then you have what is called a tensor product or a direct product. Okay. The direct product is simply written as AA, the two vectors by the side, which means now you see that there are two components here, AX, AY, AX, AY, and you have X, Y, you have X, Y. Therefore, when you expand this, there are 4 terms. AX square X, X, AX, AY, X, Y, if you write that. Write this adjoint, okay? X plus AY, Y. Now, you have 4 terms, namely AX square, XX. XX is not 1. XX, it's called a dyad. Second rank tensor is not a vector. You see here, there is only one X, but here X and X next to each other. And then you have AX, AY, XY. And you have AY, AX, YX. They're not the same. Okay? And then you have AY square, Y. Okay? This is called the second rank tensor. In 3 dimensions, second rank tensors are very important for physical quantities. Some things like that you measure. Pressure, for example, is a tensor in the real sense. It's the gradient, rate of change of momentum. It's a gradient. Therefore, you will see that it has a second rank property. And likewise, there are other tensors. In chemistry, you will come to know later when you study what are called the moment of inertia. In physics and chemistry, you will study. Moment of inertia is a second rank tensor, even though the moment of inertia that you study in your textbook will all be scalar. Okay? Angular momentum J squared by 2I is the rotational energy of a particle which is rotating with its moment of inertia I and angular momentum J. But moment of inertia is a second rank tensor. In 3 dimensions, it has 9 terms, but only 6 independent components. That we will not worry now. The point is, vectors are done like this. So what is A dot B? And what is A cross B? Okay. See, the vector X and Y, when we say they are orthogonal, okay, what we say is that the vector X dotted Y is 0. This is 90 degrees. Okay. The definition for any scalar product A dot B is the magnitude of A times the magnitude of B times cos theta, where theta is the angle between the 2 vectors. Suppose this is A. and this is B. Okay. So obviously, when you talk about the unit vector x, the magnitude of unit vector is 1, the magnitude of y is 1, but the angle between the two is 90 degrees, x dot y is 0. Okay? And exactly the same way, you can say x dot x is 1 because it's cos 0. Okay? And y dot y is 1. So this is how we introduce elementary vectors. I still haven't told you what's the relationship between vectors in different coordinate systems. That actually provides the best definition for vector, but we'll get to that later, okay? Now, this is all operational and you need to understand the basic notation and also the why we are going to do this mathematics to understand quantum mechanics later, okay? So therefore, I'll stay as, what do you call, the level at which some of you have been exposed and the others have not. Therefore, it's better to recall for those who already know and for those who haven't studied to write these things carefully, okay? Now, the cross product of a vector, of course, is very, yes, yeah, go ahead. Yeah. What is the rank? You ask me, it has to do with okay, I'll get back to you. Okay, I'll get back to you. I can't quickly remember that, but the rank relates to the properties of this when you write them in terms of other models. But anyway, I'll get to that. Right now, the rank is a specification on the nature of the vector. So if it is a scalar, we say it is of rank 0, okay? Which means it is not changing its value when coordinate system is rotated, okay? The scalar remains the same. Magnitude of this remains the same whether you used different coordinates. A vector, on the other hand, when you rotate the coordinate system, okay, the vector components change. And therefore, the new components, that is the new vectors, new components are related to the old components in a certain unique way based on the angle of rotation of these vectors. So that has to do something with the rank. And when you talk about the second rank tensor or second rank quantity, it doesn't depend on one rotation matrix, but it depends on the direct product of two rotation matrices. So the number of such rotation matrices are directly related to the number n that you put in, whether the n is 1 or 2 or 0. In the scalar, of course, it doesn't depend, therefore it's rank 0, okay? But let me get to the actual mathematical definition later, okay? I'll find out, I'll get back to that. Now, where are we? Okay, so yeah, cross product. Now, it's better to define cross product with 3 dimensions, but in 2 dimensions, the cross product is a scalar. In 2 dimensions, the cross product is given as AXBY minus AYBX. Okay? It's a number. Okay? Because AX and AY are numbers. Okay? AX and AY, BX and BY are numbers, or maybe some functions or whatever it is, depending on the nature of the vector. But the product of these is, this is for, in 2 dimensions, this is a number. In 3 dimensions, you will see that the cross product is actually a vector. Okay? And then what about the direct product? I have told you that. The direct product is this. Now, this is one way to progress with vectors and do the mathematics and study the role of vectors. But for all physics, there is another way that you represent these vectors using what are called linear algebraic models, and these are matrices. And that also you haven't studied before. We will get to that after we do the basic vector calculus, okay? So, the same thing in 3 dimensions. Let's move to 3 dimensions. Okay, now, before the 3 dimensions, suppose we have 2 vectors A, AX, X, plus AYY. To complete this, BX X plus BY Y. What is A dot B? A dot B is from the actual value of the magnitudes, it's A, B times cos theta, where theta is the angle between A and B. But A dot B is also obviously AXX plus AYY dotted with BXX plus BYY. Okay? And you know X dot X is 1, X dot Y is 0, Y dot X is 0, Y dot Y is 1. Okay? These are unit vectors. Okay? Therefore, you have this as AX BX plus AY BY, also a number. Okay? That's a scalar product for two different vectors. When the vector is the same, A dot A, you see it's AX square and the AY square. Therefore, that's the square of the magnitude of the vector. Okay? So, 3 dimensions, which is very often we end up with solving problems in that. And in higher dimension problems, you'll solve when you go to higher classes. In 3 dimensions, you have 3 mutually orthogonal vectors, which we can imagine. Okay? X. And there is a coordinate framework such that when you rotate from X to Y, the Z should be in the direction of the right-handed screw. So if you take a right-handed screw, okay, three fingers like this, if you rotate X and Y from X to Y, where does the screw move? If you go from X to Y, it goes up. If you go the other way around, Y to X, the screw moves down. So you have to always make sure that X to Y gives you Z, Y to Z gives you X, Z to X gives you Y. Please remember, if you go from Z to X, right-handed screw moves out in this direction. Right-handed, not left-handed. Okay? You move the screw. If you are moving the screw like this, what does it do? It comes out. Okay? Therefore, if this is Z and this is X, obviously Y is in this direction. So, right-handed rule is what we all use as left-handed vectors we don't use. There are other instances. We don't need to worry about it now. Okay? So, if you do this, any vector now is a projection of this vector A. Please remember, you can imagine the corner of this. This is a rectangular corner. Okay? One of them has x-axis, the other has the y-axis, and the third one has the z-axis. Okay? Which would be the x-axis if this is the z-axis? This direction, because if you move from here, what do? If you move from here, if you rotate, the screw goes up. The screw goes up, therefore that's the direction, Z. Okay? So if that's X, this is Y, that's a Z. So I'm standing somewhere, you draw from me some point of some middle point to that. That's a vector direction. Now this vector has 3 components. One along the x-axis, one along the y-axis, and one along the z-axis. Okay? So the 3 components, if you want to draw them along the x and y, it's basically some point. But then you remember this point, and this point is, the component is on this axis. What about the x component? You have to draw perpendicular to that. Okay? So you have ax of x plus ay of y plus az of z. Each one is one direction. Okay? Ax of x is in this direction, and ay of y is in this direction. So when you add these two, it will be in this direction, diagonal. And ay of y, ax plus of x, when you add that to the az of z, it will go up, and so you will get this vector. Okay? So think about how you do this. Rotation, adding the vectors sequentially gives you the final vector. So this is A. Okay? Again, you have the same relationships here. X dot x is 1, x dot y is 0, because x and y are perpendicular, x and z are perpendicular, they are 0. And likewise, you have y dot y is 1, y dot x is 0 and y dot z is 0, and z dot z is 1, z dot x is 0, and z dot y is 0. Therefore, you can see immediately the magnitude of A is the square root of A dotted with A, and that's the square root ax square plus ay square plus az square. Okay, it's a scalar. Okay, scalar. Again, here you have a clear definition of the vector product and also the tensor product or direct product. Simple question. What about the direct product? How many components do we have? How many terms do we have? AA. There are 3 here. So there are 9 base quantities. What are those 9 quantities? XX, XY, XZ. Then you have YX, YY, and YZ. So what is this one? If you take the AA, this will be AX square. What would be this? What is this component associated with this vector? X is first, Y is second. It's AX, AY. See, you write this once more and see all the 9 terms. That's what you have to do. Write this once more, bracket, okay, once more, and you take the product. So there are 3 plus 3 times 3, 9 products are there. And the 9 products have 2 of these and 2 of these. XX, XY, XZ, YX, YY, YZ, and then you have ZX, ZY, and ZZ. Okay. They have 9 quantities. Now, that's just mathematics and simple details. I mean, by and large, this is how we define this. But what's the use of these things and how do we simplify things from here? Okay, so let's first go to the original question in 2 dimensions, namely 2 vectors, 1 vector expressed in 2 different coordinate systems. Okay, theta is the angle. So we will call this x prime. I think that's what I wrote. So y prime. So now you can see that this is a y prime and this is a x prime. And the same vector, where is the, okay, sorry, this is not the one. I mean, I need to draw the vector. I've just drawn the coordinates, okay? So the vector is somewhere here. Vector is somewhere here, okay? So now you have the components of the vector here and the components of the vector here, okay? And the components of the vector in this axis system and the components of this vector in this axis system, okay? So you have the relationship, and I want you to go back and do this for yourself, okay? I have written a x here, right? This is x-axis, this is y-axis, okay? So y. The relationship between x, y and x prime, y prime. Okay, what is the relationship? See, remember, this is unit vector x. This is unit vector x prime. Okay, and this is unit vector y prime. Is that right? Yeah. this part. And we have x prime. What is the relationship between x prime and y prime and x? What is this length? It's not 1. It's not 1. There's an angle theta. Which angle? Sin theta, cos theta, which one? Sin theta? Sin theta times y. This is y. What about the x? Cos theta. So if you relate that, this will be cos theta times x prime and sin theta times y prime. Okay? You can see that. What is this? Y prime, draw this in bigger ones, y prime, x prime, and then you have x and you have y. Okay? So this vector is the sum of this and the sum of that. Okay? This is theta. This is unit length, 1. Unit vector. Okay? All are unit vectors. Okay? So if this is unit length, x is the sum of this is what? The base is what? Length times cos theta. What is this one? The height. This times sin theta. That's what that is. Okay? And exactly the next one you can write, it is minus sin theta, cos theta. I added the vector. Yeah. X is x prime plus y prime.
Sir, in the new axis, we have written A vector as A x prime capital.
No. X prime is what? Tell me. X prime, this is unit vector. The full length is unit vector. Okay? This full length is unit vector. Obviously, they won't match. The unit vector above is going to be short when you do the projection. So what is that length? What is this length? If this is 1. The angle is theta. Cos theta. Cos theta times what? No, this. This length is cos theta. So the unit vector x prime will be cos theta times, see the contribution is cos theta times the x prime is this contribution. This is 1. Up to this is 1. When does it become 1? When theta is 0. When theta is 0, x prime is equal to x. Okay? Then you can see that. If theta is 0, x prime is equal to x, y prime is equal to y. If theta is not 0, what happens to x and y? X and y are contributed by both x prime and y prime. So this length of x prime is, unit vector is contributed. This length is cos theta times x prime. Isn't it? You have to put the vector here because you are writing this vector in terms of this vector and this vector. So this is cos theta times the unit vector x prime. What is this length? Exactly the same thing, sin theta times y prime. Okay? Now, if you calculate now this quantity, namely, you have done this for x. Now this is y. Okay? So you want to calculate y in terms of y prime and x prime. Okay? You can probably do y prime is what? This is also theta. Right? If this angle is theta, what is this angle? This is also theta. So if you calculate this, there is a 90 plus theta coming in. That 90 plus theta will make the sin theta to cos theta to minus sin theta. Okay. So you see cos theta sin theta minus sin theta cos theta x prime y prime. What it means is that under coordinate rotations, you are rotating the coordinates about an axis which is perpendicular. Okay? You are rotating by an angle theta. The new coordinates are expressed in terms of the old coordinate by a matrix called the rotation matrix, which depends on only one angle. Okay? One angle, theta. Now, suppose I want to write x prime, y prime in terms of x and y, what will I have to do? From this picture, without doing any mathematics, what will you do? Take the theta to minus theta. You start from there, but you are going by minus theta. Okay? So if you put minus theta, what happens? So if I write x prime, y prime as cos minus theta, which is cos theta, and sine minus theta is what? Minus sine theta. This is sine theta. This is cos theta. Okay? In terms of x and y. So if you go from x prime to y prime to x and y, this is a transformation that takes x prime, y prime to x and y. But if you want to go back, this is the inverse transformation. Exactly the opposite of what you wanted to do. Okay? Now, if I write this matrix here, namely cos theta minus sine theta, cos theta, and write x and y, do they satisfy? How do you multiply matrices? Row to column. Cos square theta plus sine square theta 1. This one, so this is 1 cos theta minus sine theta plus sine theta cos theta 0. What about this one? 0, 1, xy. So what do you get? X is equal to x, y is equal to y. Okay? That's the inverse transformation. Yeah, go ahead. How do I?
How do you multiply matrices?
Oh, matrix multiplication. Okay, that you haven't studied matrices, right? Okay, that's why I'm not sure which one I needed to introduce first. Okay, to introduce vectors first or vector matrices first. I found both chapters are in your class 12. Okay, okay. How do you multiply? First of all, what are matrices? Just on the side, it's an array of elements. They can be numbers, functions. They can be with. See, for example, if you write something like this, A1, A2, A3, A4. You can call this a matrix with row 1, row 2, column 1, column 2. Okay, so you can say this is a matrix of 2 rows and 2 columns. And 2 columns. It's not limited to that. You can have a matrix which has only 1 column. Doesn't have anything. It's an array of numbers. Okay, the array is, it's in here, it's 1 column array. Here it's 2 column, 2 row array. You can also have 3-dimensional matrices when the 3rd column is in the 3rd dimension. Okay, then you say that the matrix is a 3 by 3-dimensional array. You can have n-dimensional array. Okay, except that you can't visualize them. But the point is these are arrays. And this is called the square matrix. You can also have matrices which are like A, B, C, D, E, F, for example. Okay, so this is what? This is a 2-row, 3-column arrays. So matrices are denoted by the number of rows and the number of columns with an into cross product. Okay, this is the number of rows. Sorry, this is the number of columns. Okay, and a square matrix is one where m is equal to n. All the others are rectangular matrices, or if there is only a column, it's called a column matrix. If there is only a row, now this is 1 row, 4 column matrices. Okay, so it's 1 by 4. Okay, this one is 2 rows, 1, 2, and 3 columns. So it's 2 by 3. So A m by n denotes the number of columns in the matrix M and the number of rows in the matrix M and the number of columns n in the matrix and the entries accordingly. Now, when you add two matrices, for example, they have to have the same number of rows and number of columns. Now, I have written like this: A, Ij, this is row number, this is column number. Okay? So you have 1, 1, row number 1, column number 2, row number 2, column number 1, and row number 2, column number 2. Okay? Any quantities. It can be numbers, it can be functions, it can be other things, it can be an array of animals. What you do with them is different. Okay? This is an array. Your class is a two-dimensional array. What is the array? 1, we'll take the last one. That considered to be a 0 entry there. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you have 13 columns. How many rows do you have? 1, 2, 3, 4, 5, 6, 7, 8 maybe. So this class is an array is a matrix array with that many rows and columns, where some columns are empty, some points are empty. For example, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. Suppose I have a matrix like that. Okay? It's a 3 by 3 matrix with 0 entries in certain columns and rows and numbers in them. Okay? So how do we add matrices? If we add matrices, we must have the same number of rows and same number of columns for both the matrices. B2, 1, B2, 2. You can't add a 2 by 2 matrix to a 3 by 3 matrix. You can't do. You can't add a 2 by 2 matrix to a 2 by 1 matrix. The number of both matrices, this is step number 1. There are special additions called direct additions, which you will understand at much, much later period when you go to quantum mechanics and mathematics and so on. We are talking about simple additions. Okay? Simple additions, the number of columns and rows in the matrices which are added should be the same. Now, on the other hand, when you want to multiply, which was a question that he asked, if you want to multiply A, B, C, D, and let me write E, F, G, H. Okay? This is a 2 by 2. This is a 2 by, say, I, J. 2 by 3. You can do that. You can multiply that. The only requirement for multiplying two matrices is the row number, the column number of the first matrix and the row number of the second matrix should be the same. Okay? The reason is the multiplication is done as row-wise, row number 1, multiplying element by element, column number 1. So if you do this multiplication, A times E plus B times F, you can't have one more row if this is what it is. That multiplication is not possible. Okay? So the number of rows, number of columns in the first matrix, left matrix should be the same as the number of rows in the right matrix. Okay? So now you can tell me what is the corresponding product. Can you please tell me? What is the first element? AE plus BF. This is column 1, column 2, row 1, row 2. Okay? So the first element is the multiplication of the first row with the first column. The second element of the product is the multiplication of the first row with the second column. Okay? So that is AG plus BH. The third, because there is a third one, it's a multiplication of the first row with the third column. So what do you get? AI plus BJ. Okay. So with that, we come to an end of the first row. Now we have the second row here. The second row multiplying the first column, second row multiplying the second column, second row multiplying the third column, give you the corresponding entries. Okay. So what do you have? CE plus DF. Then you have CG plus DH. Then you have CI plus DJ. Okay. Now, what is the dimension of this matrix? This is called the dimension. So it's 2 by 2, 2 by 3. The dimension of this matrix is 2 by 3. 2 rows and 3 columns. This and that will make the final dimension of the two matrices. Now, there is a problem. What is this matrix? E, G, I, F, H, J, A, B, C, D. Can't be defined. Okay. The reason is the number of columns here do not match the number of rows here. There are 2, so this is not possible. Okay. Matrix simple multiplication is not possible. No. There are other complex multiplication, we'll see that later, called the direct products, which is defined for all matrices. But simple matrix multiplication, when you do, you have to take rows and columns in the same order, and therefore, what is important is one of the most significant properties of these matrices, which are not in the numbers, is A, B, C, D. Suppose you do P, Q, R, S, okay? And you do P, Q, R, S, A, B, C, D, allowed, because both have the same rows and columns, okay? Now you do this, what do you get here? AP plus B, R. And then what do you get? AQ plus B, yes, okay? CP plus D, R. Then you have CQ plus DS. What do you get here? AP plus QC. BP plus QD. AR plus CS. And BR plus DS. Therefore, if you call this as the A matrix and you call this as a P matrix, please remember the product AP is not equal to the product PA. Okay? Matrices don't commute in general. You cannot commute them wrong. There are special properties that the matrices should have before the commutation happens. Okay? So, this is not true with the numbers. 5 into 5, 5 into 7 is the same as 7 into 5. Matrices don't commute. And when quantum mechanics was first discovered in the modern quantum mechanics, not the one with Max Planck, Niels Bohr and others, that's called the slightly older quantum theory, but it led to that. When quantum mechanics was first discovered, it was Heisenberg who put in properties like momentum and position of particles. He represented them using matrices, column vectors, and he found out that the product PQ is not the same as the product QP. That the momentum and position represented as operators or matrices don't commute. And the non-commutation between PQ and QP is the most fundamental relation, that PQ minus QP is equal to IH bar. Sorry, QP minus PQ is equal to IH bar was the most fundamental relation that Heisenberg arrived at.
What is IH? What is IH bar?
Yeah, I is square root of minus 1. H bar is h by 2 pi, Planck's constant by 2 pi. We'll see that. Okay, I'm just reading it out, but the operators for position and momentum, QP minus PQ, is not 0, but it's I h by 2 pi, and I is square root of minus 1, complex number. So complex numbers come in. So there are issues. And the representation of quantum mechanical quantities using matrices is the most convenient way to do all computational processes using computers. Yes, yeah.
Earlier you said we cannot multiply that 2 cross 3 and that.
Yeah, 2 cross 3, this one. See, what I'm saying is, this cannot be multiplied with this.
So instead, what if I was able to add 2 zeros at the bottom of the second matrix?
Say it again.
If I could convert that 2 cross 2 into a.
No, that's one matrix. The moment you remove anything out of it, that's not the same matrix.
How about I add zeros to that?
No, you can't. I didn't give you that matrix. You can't do that. In the simple multiplication, when you have two matrices which are given by n and some n prime, q prime, and n prime are not the same, you can't multiply them. Okay? Now, to make them, you can add zeros and other things which are, that's not part of the basic definition of when you have two matrices which are like that, whose left matrix is row number and the right matrix is row index, and the right matrices, left matrix is, the column index and the right matrix is row index. If they don't match, you can't do the standard multiplication. That's all there is. Okay? That's all there is. So now you know. So can we go back to the vectors now? Okay, it's 14:59. So we'll stop now. 5 minutes. Yeah, go ahead. 5-10 minutes and complex numbers. Yeah. Okay. I don't know the answer. Heisenberg also didn't know, but it turned out to be I. The reason is, see, when you represent, complex numbers are now essentially all over physics. I mean, initially complex numbers were thought to be very unphysical, you know. But then the question of what is the square root of a negative number? This question was asked hundreds of years ago, 200 years ago. And then the answer turned out to be that if we introduce what are called pairs of numbers and do an algebra with pairs of numbers in a certain way, then real number algebraic methods and real number processes can be extended to this, and the extension naturally ended up with the complex number domain. When you are able to define I, you define I. Exactly what is I? If you want to know, it's, you know that, isn't it? When you say I is square root of minus 1, this is a definition you have given as an imaginary number. Okay? With this definition, you can now write a number x plus iy, which is a pair of numbers x and y, and say a plus ib, which is a pair of a and b, and now extend your real algebra to include the fact that I square is minus 1. Okay? With that, you generalize the algebraic methods, the mathematical methods, to include objects which at that point of time people had no particular, reason to, but including them solved even quadratic equations, for example. If you want to know some quadratic equations, the square root of b square minus 4ac may turn out to be negative. If you write ax square plus bx plus c is equal to 0, the discriminant is square root of b square minus 4ac. What if when it becomes negative? Can you define the roots? So right from the quadratic equation roots, people needed the help to understand what is the square. Therefore, if you take the square root of minus 1, then you see b square minus 4ac is a number, and that number multiplied by the square root of minus 1, I, now becomes the root of that. So the complex numbers had their origin from the fundamental equations, from the algebraic equations and from the roots itself. And later on, of course, you saw that it was beautifully extended to the mathematics, and complex numbers are so important today that we don't even think about why there is square root of minus 1. It's there. Okay? In a way, you can't tell what is 1 and 2. It's your conception of what is 1 and 2. Okay? The numbers, as you tell them, 1, 2, 3, 4, etc., are your constructs. Okay? Do they exist? You don't know. Do numbers exist? Not from the representation of what they are. Do numbers as abstract quantities, do they exist? Ask Balakrishnan next time. Okay? he'll give you the right answer. Okay? So, things that we think we know or we take for granted. When we say mass, how do you define the mass? Some quantity? Does this room, when all of you leave, does this room have a mass? You can't see. The air has a mass in it. Okay? And the mass, the air's mass is not because it occupies this much room. If the same amount of air occupies a smaller room, it will have the same mass. But how do you define mass? And how do you define 1 kilogram or 2 kilograms or 3 kilograms? What is 1 kilogram? What's 1 kilogram? That's your weight, right? But who's told you that that's 1 kilogram? Many years ago, compared to some standard weight held in 0 Celsius, 1 atmospheric pressure, isolated, coal, platinum and iridium, certain mass. That was definition long, long ago. Today, mass is not defined in terms of that, because the moment you define these things in terms of the real quantities, these quantities can decay, destroy over a period. Therefore, the unit will not be standard. Therefore, all the fundamental units and weights and other things, the SI units, are now defined in terms of fundamental constants. Constants like the velocity of speed of light. What is a meter? The meter is not a certain rod kept in Paris or whatever. The meter is now related to the speed of light. The distance traveled by light in X number of seconds. What is that X? 1 by whatever that number you have. 2.9929. 2.99. How many nines? 2458 is the last 4 digits. 2.99792458. Okay? 8 digits today we have. So that times 10 raised to 8 meters per second, isn't it? Is the distance traveled by light in vacuum in 1 second. Invert that, you will get the distance. Okay? That's the definition of the meter. The distance traveled by light in that seconds. So today, all the fundamental units are useful in defining what we call as standards. So in the same way here also, complex numbers are so useful. Once you know I is also associated with the general formula by Euler on the exponential. You remember this formula? Cos theta plus I sin theta. It's a very famous formula, okay, for the complex number. So if you do this, now, what is square root of e to the I pi, I theta? E to the I theta by 2. So you write it as theta by 2. And that. What is square root of I? No, square root of I. Okay. E to the I theta is this. From this, what is I? When theta is 90 degrees or pi by 2, what is this one? E to the I theta is I. Okay. So now, what is square root of I? This is e to the I pi by 2. Okay. So what is square root of I? That. Okay. What is that? Cos pi by 4 plus I sine pi by 4, right? Cos pi by 4 is how much? 1 by root 2 plus I by root 2. Okay? Take the square of this. What do you get? 1 by 2 minus 1 by 2 plus 2I by 2, so which is I. So the square root of I is e to the I pi by 4. So what is the fourth root of e to the I pi? Square root. Everything you can define now. The moment you know this Euler's formula, you can define all these things. What is I squared? Of course, all of you know I square is e to the I pi. That's minus 1. Okay? So complex numbers have become useful in every domain today, physics, engineering, technology, everywhere. And complex numbers are useful in defining the fundamental theorem of, one of the fundamental theorems of algebra in terms of the polynomial of order n possessing n roots. And when roots are complex, they will always occur in pairs. That is, complex pair. And x plus iy, if that is a root, x minus iy will also be the root. Okay? Complex numbers, if they occur as roots, they will occur in pairs. So these are very useful. And what we'll do, we'll come back. I think you need a break for about 10 minutes. Come back at 15:20. Okay? You can just disperse now if you want. Go to the washroom, drink water, whatever you want to do. Okay? So I'll finish by 4:10, and then you'll have tea. There's one more lecture. The speaker who gave the lecture in the morning has expressed interest in continuing. Okay? So you'll have that lecture. Okay? Yeah, go ahead.